3.3. The derivative of the exponential function, e to the x. This one we actually talked about earlier in the semester. If I were to graph e to the x, it looks like this right here. Has a horizontal asymptote, y equal to 0. And if you recall that we actually drew the tangent line right here. This is not to scale. I'm a little bit off. Let me see if I could fix that. I should have actually, so yeah, it looks like that. The slope of that tangent line, we just said it basically in passing, is 1. It has a very nice property. If you were to consider e to the x right there at 0, the slope of the tangent line is 1. So what this does, it allows the derivative to or the limit definition of the derivative to simplify out really nicely. So the derivative of e to the x is e to the x. I know I did not stutter there. The derivative of e to the x is e to the x. So this is probably the easiest derivative, emphasis on the e right there. The derivative of e to the x is itself. So, but be careful. Maybe just kind of a side note. The derivative of, if I were to take the derivative of e to the x, it is not x e to the x minus 1. Why might you do that? Power rule. Power rules are for power functions. Power functions have a variable base and a real number exponent. Exponential functions have it reversed. A real base, positive constant not equal to 1, and a variable exponent. So just keep in mind that you do not use the power function for e to the x. So in 24, what we're going to look at is the derivative of 9 e to the x. Oh, because, let me just ask this. I see a constant here. Is the derivative just 0? No, that's a constant multiple, not a constant function. So the derivative here is simply 9 times the derivative of e to the x is e to the x. So the derivative is just 9 e to the x. (25). Just as an example where you have a different variable. This time, the derivative with respect to t, remember t is our variable, of e to the t. You may need to phone a friend on this one. Phone home? Okay, never mind. Et? Okay. What is the derivative with respect to t of e to the t? If you think you know, just say it. E to the t. Very good. And then if we look at 26 right here, we have the sum and difference rule that we can use. So we could take the derivative of this first part, and then we could take the derivative of that second part, and then we can add them together. So if I take the derivative of pi e to the x, anyone think they know the part of green? What's the derivative of pi e to the x? It's going to be pi e to the x. And what is the derivative of e? How many say 0? How many say 1? How many think this still looks too easy, but I'm nervous? That seems to be the rest. The derivative of e, remember, e is 2.7 approximately, is 0. Again, if this throws you off, just remember that e is approximately 2.7. The derivative of 2.7, a constant, is 0. So the derivative here is just going to be pi e to the x. All right, one last closing thought in our last minute. If you think about this, I just want to take another idea from this one. Just a kind of preview of something. So we have let's consider the derivative of 2 to the x. Technically, we won't do this till the next test, but I want to start showing you something. Its derivative is 2 to the x times ln of 2. But notice, look at this pattern. The derivative of e to the x was what? E to the x. The derivative of 2 to the x is a 2 to the x times something else. Realize that this something else is technically here. ln of e is just 1 there, which is also why we're related to that as the slope of 1. So again, you don't need to know this yet, but I just want to start kind of sowing some seeds for later in the semester to say this is probably my favorite word of the year, sowing seeds, because that is literally what you're doing at this point of your life, is you're sowing seeds for your future. But hold on to that idea that there is an ln of e here, and that will show up again with other exponential functions later in the semester. But that's a good stopping point. If you have any questions, feel free to stick around. Otherwise, I'll see you tomorrow. So there is something I'm going to sell you here. Get it? The product rule, sell it? Okay. So limits were easy because you can just do the limit a piece at a time. Derivatives a little bit more complicated. Let's consider an example. If you consider the derivative of x times x, realize x times x is x squared. And we've worked with this a few days. What is the derivative of x squared? Anyone? 2x, correct. Down here below, the derivative of x is going to be 1, and the derivative of x is also 1. So if we do the derivative of x times the derivative of x, what we end up with is 1. Notice, though, that these are different. So unfortunately, the derivative of the product is not the product of the derivatives. So it makes it a little bit harder, but maybe just to say it another way, the derivative cannot be broken over a product. So it's not as easy of just saying, take the derivative of the first thing, then the derivative of the second thing, and multiply them together. We must use the product rule. There's a couple of different ways the product rule is written. So the product rule, if u and v are differentiable functions of x, that is to say they're just placeholders for something more complicated. So just that's just one notation. Their product is also differentiable, and let me zoom in here. The derivative of u with times v is going to be u times the derivative of v with respect to x plus v times the derivative of u with respect to x. So you're going to just take each combination. You're going to take, so essentially what you'll do is you'll just write down u, multiply it by the derivative of v. Then you're going to add to that, just write down v, multiply it by the derivative of u. In prime notation, this would just be f times g prime plus g times f prime. Or using words, you could think about this as the derivative of the product is the derivative, or let me write it like this, is going to be the first times the derivative of the second plus the second, no derivative, times the derivative of the first. So I feel like I'm being very pedantic there, but however you use it, whether you're using the differential notation, the prime notation, or just understanding about it in words, it is not as easy as just doing the derivative of the first times the derivative of the second. This rule is essentially algebraically derived from some properties using limits. So if we were to actually go through the computation, we would use limit rules to go ahead and get to this form. You're not going to be asked in this course to prove it. You'll just have to be able to use the formula. So let's go ahead and get the hang of this. Let's do a couple together. Let's see what we got. Ooh, we got 4 together. Man, I'm really trying to sell you on this product rule. Such a lame joke. Most of them. It's all right. All right. So if we look at 27, Notice that this is a product of two functions. It's a product of a quadratic function and it's a product of a cubic function. Agreed? So, the derivative here, y prime, I'm going to go ahead and color the first ones just as we get the hang of it. I'm going to go ahead and do the first in green and the second in blue. So it's going to be x squared plus 1. Then I'm going to multiply it by the derivative of this blue one. So this is going to be 3x squared. I'm going to just put plus 0. Then we'll have plus the second, which is going to be x cubed plus 3. And we're going to multiply it by the derivative of the first, which is 2x plus 0. So again, this right here, if you think about this as, u and this one is v, this is u times v prime plus v times u prime. Is everyone okay with where I got that red, green, and blue line? Okay, so that's the product rule. So just to go ahead and finish this out, I'd recommend simplifying this. So I'm going to write this all in one color now. So this is going to be x squared plus 1 times 3x squared plus x cubed plus 3 times 2x. You will want to go ahead and probably simplify this, that is to say multiply things together, because while we're not doing it here, the kind of the future thought is we're going to need to figure out where there are horizontal tangents, or maybe we're going to have to find out where there is a certain change that allows us to optimize a certain object. So I'm going to distribute this, so I end up with 3x to the fourth plus 3x squared plus, distributing here, is going to be 2x to the fourth plus 6x. So when all is said and done here, we'll have y prime is equal to, let's see, we got 5x to the fourth plus 3x squared plus 6x. So a little bit lengthy, but that is how the product rule plays out. Does anyone have any questions on 27? All right, so 28 is going to be one involving a linear function and is being multiplied by e to the x. Let me throw caution to the page right here. Get it? Caution to the wind, caution, yeah, whatever. The derivative is not 1 times e to the x. It is not 1 times e to the x. Why might you do that? What's the derivative of x? 1. What's the derivative of e to the x? So you might, and this is, again, if the test is multiple choice, I haven't written this year's version of the test yet. This would probably be one of the distractors. So this is wrong. So just a little bit of a caution. It is not as easy as just taking the derivative of the first and multiplying by the derivative of the second. You need to use the product rule. So I'm going to go through another one, but I'm going to just do it a little bit faster this time so you can kind of see the flow. So the derivative, y prime, is first times the derivative of the second plus the second times the derivative of the first. You may off to the side do something like the derivative of x with respect to x is 1, and then the derivative of e to the x with respect to x is e to the x. You may do that off to the side just to help yourself out. But this is going to be, but you can see that this is u times v prime plus v times u prime. So y prime here is x e to the x plus e to the x. Okay. So there's two basic examples involving the chain rule, not chain rule, getting ahead of myself, product rule. Any questions on either of those? All right. Say, did you need to see that still? Okay, you're good? Okay. All right, so we have two examples right down here. On 29, I'd recommend to do something with this 1 over x first. In this case, I'd recommend y is equal to x to the negative 1 times x squared plus e to the x. Have I taken the derivative yet? No, I've just done a quick little algebraic step to make it easier to use the power rule. Let me go ahead and give you a moment to try 29. And before I actually let you try those, I'm going to also set you up for 30. If we look at 30, we have y is equal to e to the 2x. But that is a composition. We haven't talked about the composition yet. But remember that you can write this as e to the x plus x. And anyway, everyone agree that 2x is the same as x plus x? And then by the rule of the addition rule for exponents, I can rewrite this as e to the x times e to the x. So you can see it is a product of two e to the x's. So let me go ahead, while I take attendance, go ahead and give your pencil a shot at 29 and 30. I'll go ahead and show the work here in a sec so you can check your work, and then I'll say a few more words about 30. So go ahead and try those two. We got to this part on 29. If you got there, just give me a quick little wave. Doesn't look like everyone. So let me just kind of pause here and we'll take a zoom in here. Does anyone have any questions? Maybe let me say this. So this is going to be so this is first, if you consider like this is u and this second part right here is v. This is going to be u times the derivative of v plus v times the derivative of u. And then I just simplified back to get to our standard form we started with. So you can see the x squared went back to the denominator, the negative multiplied with a positive to make that negative. You probably could have gone a little farther here in terms of just if we need to go ahead and simplify in the future. Remember that 1 over x could be distributed and you get 2x over x plus e to the x over x. And then you can distribute this through and you would have negative x squared over x squared minus e to the x over x squared. Because if we did that, we can do some simplification with the division, giving us 2 plus e to the x over x minus 1 minus e to the x over x squared. So if you then combine the constants, you would have 1 plus e to the x over x minus e to the x over x squared. So not necessarily required in this scenario, but just kind of review some algebraic ideas that you're probably going to need at some point in this semester still. So does anyone have any questions on this first one? Okay, in the case of 30, so if we look at this right here, this 2 to the x, this is going to be a composite function, but we don't have the tool used for the composite function yet. What we would technically do is we would need something known as the chain rule. So the chain rule has its own section. That's in section 3.6. So we'll get more to we'll talk about the chain rule on the next test or for the next test. But we do know algebraically we can go ahead and just manipulate this to get e to the x times e to the x. So to find the derivative is going to be first times the derivative of the second plus the second times the derivative of the first. So this is e to the x times e to the x plus e to the x times e to the x. So what we end up with here is e to the 2x plus e to the 2x, or 2 times e to the 2x. So again, just undoing that algebraic algebraic move to go ahead and get the separate product, we just basically resimplify everything. How many got 2e to the x? Anyone get that before me? A couple of you, very good. Any questions so far? So let me call out something to get you ready. Where do you think this 2 came from? Notice we still have this idea of like the derivative of e to the x is still e to the x, or in this case, the derivative of e to the 2x is still e to the 2x. Where do you think this 2 came from? It's the derivative of the inner function. So notice that this 2 to the x, this 2, I shouldn't say, this is the derivative of the inner function. The chain rule is really not hard in terms of the concept, but the functions look weird, making it a little bit hard to grasp sometimes. But basically, it boils down to you take the derivative of the outer function, leaving the inner function alone, and then you multiply it by the derivative of the inner function. So that one sentence is all of section 3.6. A lot of different practice at that point, but for now, we can just use the product rule. I think one of your peers asked me like a shortcut to something like this in section, what was that from Cadence? 3.1 or 3. It may have been from 3.3, where you have a 3x right here. So maybe just what if we have problem 30b, y is equal to e to the 3x. If you recognize that pattern there, hopefully you wouldn't need to use the product rule twice. You can just quickly say the derivative is e to the 3x times 3, or 3e to the 3x. So that's a little shortcut if you are using the idea that we just looked at 30. If you don't recognize that pattern, well, you can always just do the product rule twice. You can do the product rule, treating the first product rule as the first 2 as a product that you'll need to take a product rule while taking another product rule. A little bit of an exception case going on right here. And you're like, not in your dreams. I'm like, well, you're right, but in the homework. Okay, I'm trying way too hard to get an inception joke in there. Forget it. Any questions on the product rule? Looks like I already wore you all out, and we're not even done. So take a breath. That's really more for me than for you, but feels good. And let's talk about the quotient rule. The quotient rule is going to have some similar ideas. Just as you can't take the derivative of the product one piece at a time, you can't take the quotient rule one of the numerator and the denominator separately and divide them. The quotient rule is as follows. Just to make it clear, this down here is a v and the numerator is a u. You may also, the quotient rule is as follows. The v squared is going to be in the denominator of the derivative. And then you'll have u times v. Do you guys prefer prime or differential notation? Prime? All right. So I'm going to abuse notation a little bit. So it's going to be u times v prime plus, minus v times u prime. Because it's minus, order matters here. In the quotient, or in the product rule, it didn't matter, like if you did first times the derivative of the second, plus second times the derivative of the first, or put the second times the derivative of the first, or whatever. So if we look at this, sometimes I found it easier, and students will hold on to it, if you think about this as like low and high. So you could write this as technically like, you would start this as like low times the derivative, so d high. So d high meaning derivative of high, minus high times d low over low squared. Sometimes I've seen people hold on to that because there's a little rhyme that some people may have heard if you've taken a calculus before. Low d high minus high d low over low squared you go. Kind of just rolls off the tongue. And if you don't know that, I mean, I'll say it again, low d high minus high d low over low squared you go. Or if you think about life, usually you start on the ground. You start kind of at the bottom and you have to work your way up, right? So start low. In other words, you start with low, then you do the derivative of the high, minus then the high, the derivative of low. And then just remember in the future that the low where you started is your foundation. So low squared. Yeah, Destiny.
I'm so sorry. Wouldn't the low be high? Wouldn't it be high times derivative of the low according to the
Hold on. Did I write this correctly? So low d high minus the high. Hold on. See, this is how I remember it. So did I write this incorrectly? I did write this incorrectly. So let's make a correction. So I kind of tried to be too proper, too fast. So is everyone okay with this? This is how I typically remember it. So let's correct this right here. Thanks, Destiny. So that we start low. So low would be V, and then we would have U prime minus U times V prime. Good catch. Very good. This is typically how you're going to hear me teach it, just because I kind of remember it in terms of low d high minus high d low over low squared we go. Or I always think start low. Thank you. Sorry, everyone. All right. So let's go ahead and do 31 and see how that works. So this is going to be high. This is going to be low. So the derivative, y prime, in the denominator of the quotient rule will be the t cubed plus 1 all being squared. Then we would have t cubed plus 1 times the derivative of the high. So this is going to be 2t. Minus the high, which is going to be t squared minus 1, times the derivative of the low, which is going to be 3t squared. So that is the quotient rule in terms of just applying the above formula. The rest would just maybe do a few steps of simplification. So this was low, d high, minus high times d low. Simplifying this a little bit, we get y prime is equal to, 2t to the fourth plus 2t. And then you may want to do this in two steps. Like if you're okay with doing the negative and the distribution, you can. But if you're not, just take your time. So it'll be 3t to the fourth minus 3t squared, and then distribute the negative on the next step. So we would have t cubed plus 1 still all squared. So if you chose to distribute the negative on the next step, you could. So maybe doing just a little bit kind of in my head here. This is going to give you a minus 3t to the fourth plus 3t squared, just to not have to write as much. So this is going to give you some like terms. So you'll have the 2t to the fourth minus 3t to the fourth, and you'll have the 2t, and then you'll have the 3t squared. So let's see what that looks like all simplified. We would have minus t to the fourth plus 3t squared minus 2t, and all of that divided by t cubed plus 1 all squared. But that's the quotient rule. None of these are going to be provided on the test because, again, you just need to make sure you have them mastered to just kind of not have to refer to it when we do problems in the future. So it is one of those that make sure you spend time committing that to memory while you work through the problems. So right here is the answer. Does anyone have any questions on this one? Okay. So in the case of 32, we have a similar idea. You probably could do this based off of the trick we used last time. Anyone? So before we even do this, does anyone think they know the derivative? Just kind of based off of it? I heard from you, Destiny. Let me check on someone else. Plus, I know you know the chain rule based off of our conversations. Well, the shortcut here is going to be e to the minus x, and then what would I multiply it by? Destiny, you think you know? You would multiply it by the derivative of the inners. So when I expect, my answer is going to probably be e to the minus x. Again, I'm not assuming you know the chain rule right now, so you can use the quotient rule here by just rewriting this as 1 over e to the x, and then using the quotient rule where your high is 1 and your low is e to the x. Let me give you maybe 20, 30, probably 45 seconds. Go ahead and see if you could work through the quotient rule in the context of 32. So here's all the work associated with 32. In red is where I took the derivative. So you can see the derivative of 1 is 0. So when we did the d high, we have the 0. And then we have minus 1 times the derivative of the low, which is e to the x. And this disappears. And then you can see e to the x is in the numerator, and we have 2 in the denominator, so we could cancel one of them. And we get the answer we expected if we just kind of applied the pattern recognition to what we did above. Anyone get that one right? Anyone? Awesome. A couple of you. Very good. So if we look at 33, looks fun, right? We're going to do the quotient rule. And while we're doing the quotient rule, someone's going to come up and sell us the product rule. So if you think about this, don't write this. I just want to go ahead and kind of give you kind of a thought or something to pay attention to. Overall, I'm not that mean. Would I really do this to you? Well, maybe in your homework, but on a test, no. But let me kind of point this out. If you use the quotient rule, what we would end up having to do is we would have x to the fourth. Don't bother writing this, just to want to show you something. So we would have the low squared, and then we would have so with low d hot, so we would have then x to the fourth. But then realize what we would have to do is do x to the minus 1 times x squared minus 2x. And while we're taking the derivative of high, we would have to use the product rule there. So then all of a sudden, that would expand into 2 more terms. We would have minus the high, which would be x minus 1, times x squared minus 2 times d low, which would be 4x cubed. So you can imagine that there's a lot of work, there's a lot of terms. Simplifying that's going to be a pain in the butt. So this is the hard way. I would say this is the hard way. My suggestion, always do some algebra first if you can. You can FOIL the top and you end up with x cubed. So first, x cubed minus 2x squared inside minus x squared plus 2x all over x to the fourth. So right here I have, let's see, x cubed minus 3x squared plus 2x over x to the fourth. So that is a lot easier than the product rule right there. Just go ahead, FOIL things out, and not too bad, right? Still have to use the quotient rule. Or do we? Whenever you have a fairly simple denominator, remember that the denominator divides by each thing in the numerator. So again, no calculus yet. Just rewriting this as x cubed over x to the fourth minus 3x squared over x to the fourth plus 2x over x to the fourth. And some basic algebra gives you x to the minus 1 minus 3x to the minus 2 plus 2x to the minus 3. Do I even need the quotient rule here? These are all power functions. That is to say, the variable is in the base, and you have a real exponent. So the derivative here is just going to be minus x to the minus 2 minus, well, we'll do plus 6 x to the minus 3, and then minus 6 x to the minus what? 4. Just give everyone a chance to write. Technically, we should then get back to our negative exponents, but I just wanted to use this to illustrate a quick algebraic observation will greatly simplify the problem. Any questions on this one? So a lot of mechanics today. We have one more page in 3.3, so we're not going to get into 3.4 today. 3.4 is going to be more conceptual. So let's go ahead and finish wrapping up the mechanics of 3.3, then we'll go over to exam debrief. So if you realize, I alluded to this last time, the derivative of a differentiable function is a function, and you know what? If you have a function, you can still try to differentiate it. So the second or higher order derivative is just saying keep taking the derivative. Really simple idea. If you start with a function and you get its derivative, you would just label that as f prime of x. Or you would just say y prime, or here, let's put it like this. Y prime or f prime of x, depending on whether you're using y and x or your function notation. And if that is also a differentiable function, then its derivative, y double prime or f double prime of x, is also a function. That function that we just said right here, the function there, is called the second derivative. Very tricky naming convention here, right? The notation may also be in this one right here. This is the second derivative with respect to the second dimension of x. This will make more sense in the next context where we talk about it in the next lesson where we talk about it in terms of velocity and acceleration and higher, basically in motion. And by the way, you could continue this process. If f double prime is differentiable, then its derivative f triple prime of x is the third derivative. And this process continues until you get basically it could continue forever. At some point it becomes trivial. But for higher orders, you would just do f and then you'd put, kind of like the inverse notation. Let me kind of make this smaller. You would just do f, and then you would put in parentheses n of x. So instead of saying f triple prime, you would say something like f super 10 or something like that. It's just a notational convention. Or you would just say, this is the nth derivative, or for example, if n is equal to 100, it would be like f 100 of x is the 100th derivative. So, man. 100 derivatives on a test. Not as bad as it seems. So 35, we're asked to find the derivative of all orders for this function right here. So y is equal to, let me just do it over here. So y is equal to that x cubed minus 3x squared plus 2. So y prime is equal to 3x squared minus 6x plus 0, right? Y double prime would be what? 6x minus 6. Y triple prime would just be 6. Y super 4, or the fourth derivative, would be 0. And from here on out, we would just go back and get 0 every time. Agreed? So really, at that point, there would be no more new information gained about the function, so you would just stop at the fourth derivative. In the case of 35, we're asked for the 50th derivative of e to the x. Oh my goodness, so many derivatives. Anyone think they know? If we took the derivative of e to the x 50 times, we would end up with? Oh man, you're all so good. Look, you're so fast. It's not about fast, it's about understanding. But we have one more right here. The 101st derivative of e to the minus x. Anyone think they know? If you ever run into a problem like this, just try a few derivatives. The first derivative of e to the minus x is minus e to the minus x. The second derivative of the e to the minus x is going to be just one more derivative of the one we had, which introduced another negative, so it's back to e to the minus x. If you continued, it's just going to repeat. So it looks like we have a pattern. So again, we have a pattern. So the 101st derivative of the 101st dimension of x of e to the minus x, is it going to be the positive or the negative one? Negative. Why did you say negative? Because it's odd. So again, it's going to end up being e to the minus x right here. Question? Dustin? No? So again, recognize patterns, especially if you're asked. I'm not going to ask you to like take a derivative 200 and like 12 times unless if there's a pattern. So typically with exponentials and trees. Any questions on this one?